Recently, I've been refurbishing my hydroponics system, and I've been wanting to make an upgrade. This is an ebb and flow configuration, meaning these tubs fill and drain repeatedly. I have a water level sensor that controls when the pump turns on, and draining is controlled by cracking this valve. What I don't like about this setup is that the tub fills very slowly because the drain is always open while you're filling, and they drain slowly because the valve is never fully open. I would like to have an electrically actuated valve on the drain so that filling and draining could both be done at full speed. For these 3/4 inch pipes, I could probably just buy something like a sprinkler valve, but I think it'd be fun to make my own. My first step is to define what I need the valve to do. I'm looking for something that can stop the flow of water without needing to do any regulation. The flow should be unimpeded when the valve is fully open, but some leakage is allowed when closed. The leakage can be a few drops and not more than a trickle. The pressure is going to be really low, just a couple feet of head pressure at most. The valve will need to be electrically actuated. I'll be controlling it with an Arduino, and I'll need to be able to command it fully open or fully closed without any need to do intermediate position control. Manual operation will not be required. If I need manual override, I can do this with a switch. Something to keep in mind is that debris will occasionally show up in the water, like roots or expanded clay pebbles. These need to pass through without causing a jam. Finally, I'd like my actuator to not consume power while it's just holding its position. With the requirements in mind, I start looking for reference designs. I'm not looking for any CAD files to print, just ideas to help me come up with my own solution. I'm looking for something with a simple construction and suitable for 3D printing. The seat valve looked promising, but the gate valve is what I'm going with. It seems to have the simplest construction, and when it's fully open, there's no impedance to the flow. Gate valves come in a couple varieties, including some where the gate is either wedge-shaped or flat like a knife. The flat gates typically have the simplest construction, but because I'm 3D printing the valve, I can afford some slightly more complex geometry. A wedge shape is supposed to seal better, but with all the layer lines in my 3D prints, I don't anticipate amazing performance. I could consider using a sealing surface other than the bare plastic, such as a thin sheet of rubber, but that will add a significant amount of complexity to the build. I'll make a simple version first to see if that's necessary. Hopping into SolidWorks now, the first part I'm making is the valve body. I'll be modeling the negative space within the valve and then using the shell command to invert it. I start with the pipe interfaces, then move on to the wedge shape. I add a little extra room here on the bottom to ensure the gate seats properly against the sides. I also make sure there's clearance on the sides at the top. The gate will have some tabs on the side to help guide its motion. I'm not entirely sure these are necessary, but I've seen them on other valve designs. Extruding this top profile up gives the gate room to move out of the flow. Then I shell the part outwards to turn the solid body into a cavity. Now I'm creating the gate part using dimensions that I exported from the first part. I create an assembly to see how the parts look together. The gate will be raised and lowered with a threaded rod, so I create a placeholder part for that. Then I model the hole for it and some nuts on the gate. A flange on top will hold the cover on with a series of bolts. I start modeling the valve cover by replicating the flange. Here I'm manually copying the dimensions, which isn't a robust solution. Another way to do this would have been to model the whole valve as a single part and then use a split operation to cut the top off. I toss a hole for the rod in the center, then see how it fits in the assembly. I mate the cover to the body with a gap to represent the gasket I may use. I include the hardware in the assembly to make sure the lengths are acceptable, and to remind myself I'll need screwdriver access as I add more features. The motor I'm choosing to use here is one of a few that I already had on hand. Of the motors I have available, I chose this because I know it has enough torque to do the job, and the shaft is the easiest to interface with. Here I'm modeling a placeholder for the shaft coupler hardware. Now I'm looking at how the motor is positioned and thinking about where the wires will be routed, how the gears will be shaped, and what sort of loads the print will experience supporting the weight of the motor. Now that I've positioned the motor roughly where I want it to be, I can model some geometry on the valve cover to hold the motor in place. A simple fork with 2 mounting holes should be adequate for a proof of concept. You'll notice there's no seal on the rod. I expect my first version of this valve to leak through there, and I'll address that in a second version if necessary. For the gears, I just grabbed some models from McMaster and I'll modify them to connect to my hardware. The chamfers I put on the gears are to improve the print quality. My printer elephant foot's pretty bad and this chamfer helps reduce that. When I'm deciding how far to space the gears, I'm keeping in mind all the printing defects I can expect that would cause a jam if they're too close together. The larger gear will get a chamfer as well as a pocket to hold a nut. The last part that I need to make is just a retainer that will keep the gear on the rod. This will make it so that as the gear rotates, it causes the rod to be pulled up or down rather than the gear itself climbing up the rod. So here's the final version. I added some supports down here for rigidity, and I turned this little retainer at an angle so it wouldn't block these screws. I also made the retainer screw together so that way it could actually be disassembled after being assembled the first time. And here's a little exploded view. I printed all the parts, glued the retainer onto the valve cover, installed nuts, made a simple gasket, and gave the gate a little sanding to improve the seal. Now I'll let the assembly time-lapse play so you can see how it's put together. Now I'm testing out the motor here with 5 volts from my power supply. The gears seem to be meshing just fine. The way the motor mount printed resulted in a slight tilt inwards, but it's not causing any jam. Here you can see the gate moves quite slowly. There's no specific speed requirement, and this should be just fine for my hydroponics. There are ways I could change the speed of the gate, such as changing the gearing ratio and choosing a rod with a different thread pitch. And in general, if I get the gate to move faster for the same motor RPM, then I'm losing torque that I could be using to seal the valve, so it's a bit of a trade-off. More torque would seal better, but I may actually want less torque from the motor based on how my controller turns out. Here's a sped up clip of it closing. Notice how the retainer here bends when it closes. I'm hoping to detect the increased current draw as this happens to shut off the motor. Now about the controller. The motor needs bidirectional control, so I'll use a generic H-bridge module that I already have on hand. The real challenge here is how to know when the valve has been open or closed. Normally I would put a limit switch, and in this case that would work fine for opening the valve, but when it's closing I want it to really seat firmly into position, and I don't think I could achieve that if I have it stop just when it touches a switch. So instead I'm thinking I'll monitor the current draw of the motor. This approach would also mean there are fewer mechanical components that could fail, which is entirely possible considering that this will be sitting outside in the elements for potentially years. Not that SoCal gets harsh weather, but the fewer wires and mechanisms the better. My original plan was to just put a resistor on the ground side of the motor driver and measure the voltage across that to estimate the current draw of the motor. However, after some feedback, I decided that wasn't the most ideal solution. My worry was that perhaps this would change the motor driver's ground voltage and interfere with the digital logic. Anyway, I remembered that I have an unused current sense chip, so I decided to try that out for the first time. This chip will let me measure the current and certainly won't interfere with the digital logic. If everything goes smoothly, I can switch back to the other solution and save this chip for future use, but it's better to start off with the solution that's less likely to have problems. Now I'm wiring up the circuit like the block diagram shows. For the most part, I'm just connecting off-the-shelf modules together with jumpers, and the only circuitry I needed to put on a breadboard was a passive RC filter. This filter will do my signal conditioning for the purposes of benchtop testing, but I'll likely use something more complex before installing the valve in my actual hydroponics system. I also add a couple buttons for the Arduino to control opening and closing the valve. The only problems I encountered here were that I apparently forgot how this H-bridge module works after not having used one in over a year. The diagram shows a speed and direction pin, but that's not really a good description of the pins. But that really only impacted the software, not the wiring. I wrote a simple Arduino program to rotate the motor open or closed in response to the buttons, so I could begin evaluating the current sense chip. There's no logic yet to detect if the valve has hit a stop. I'm showing a graph of the voltage output of the current sense, and you can see how it changes in response to me adding resistance to the motor with my hand. I can very easily feel that the assembly will tear itself apart if the motor is allowed to run without some algorithm to turn it off. The signal from the sensor is just barely strong enough that I should be able to develop an algorithm for benchtop testing, but I'll need something more robust before I deploy it. Here you can see the response as the valve closes. You can see the retainer flex and the voltage creeps up a small amount. It's a very small change on this graph, but it's just barely enough for the Arduino to detect it. Now for the algorithm. My first iteration is going to assume ideal conditions and not consider any fault cases. I'll have it simply monitor the current and shut off the motor when it exceeds a threshold. To reject noise and to ensure the valve is firmly seated, I'll require it to stay above the threshold for a short amount of time. I'll use the same technique for opening and closing the valve, but I may use different timing values. I notice the current spikes much faster when it hits the open stop because there's less flexibility in the assembly in that direction. Here's my first attempt at running the algorithm. Like before, I have the voltage displayed from the oscilloscope, but I also have the Arduino serial monitor visible. The number constantly streaming is the ADC value, and next to that number will appear the number of samples which have exceeded the threshold limit. Once 5 samples have exceeded the threshold, the motor will turn off. The algorithm does correctly stop the motor despite some unexpected console output. Here's that console output again. You can see that after 5 consecutive samples above the threshold of 506, the motor stops, but for some reason it didn't print the count correctly. I do want to figure out why it did that, but it's not the roadblock yet. With the controller showing potential, I dug up some power supplies I didn't mind dedicating to the garden. I have a 5V 1A supply for the Arduino and a 12V 2A supply for the motor. Using separate power supplies will prevent noise from the motor from propagating back to the Arduino, and it'll prevent the Arduino from losing power if the motor draws too much. I organized the circuit into a user input module, a sensing and driver module, and gave the Arduino a shield to connect them all. This will all be DIN rail mounted in my hydroponics control cabinet. Now heading outside to install the valve. The first thing I have to do is remove the old controller. It uses a discrete circuit rather than a microcontroller to switch the pump, and I'll be replacing it with a new relay board that's controlled by the Arduino. It's a little nerve-wracking to replace the old controller that's worked perfectly for years, but I built this cabinet years ago specifically to accommodate this change. I think one reason it remained functional so long is that it was completely sealed from the outside environment. I opened it up to remind myself how the circuit worked, and the board was in pristine condition despite the weathering that occurred inside the cabinet. While the cabinet does keep rain out, there's still a giant hole in the bottom for cables to enter through. The shadows of the DIN rails on the cabinet door are just due to aging of the wood. I gave the new relay board a waterproof coating, but I'll definitely need to seal the cabinet a little better for the rest of the electronics. All of these modules snap onto the DIN rails using parts I 3D printed and glued onto the backs of the modules. It's a simple snap-on design that I copied from Phoenix Contact. It feels secure enough for now, but I do expect the hot glue to become brittle over time. All the modules with protoboard are mounted on MDF, which I expect to degrade over time. I anticipate replacing them with something that'll hold up long term. The Arduino gets installed near the pump relay and the two are connected. Next, I drill out a hole for the float switch cable, which had previously just been jammed through the cabinet door frame, and then I discover the walls are too thick to use a cable gland. Regardless, I connect the cable and move on. At this point, I'm testing that the Arduino is able to replicate the behavior of the old controller. When my magnetic float reaches the top reed switch, the pump turns off, and when it reaches the bottom reed switch, the pump turns on. Luckily, I guessed the pin assignment correctly for the reed switches, and it worked first try. This Arduino will be controlling both the pump and the valve. Next goes in the motor circuitry, then the user input, and the connections. Now I'm going to see how well the valve performs at controlling the flow of water. I temporarily install it in a convenient spot. The controller is in manual mode, so I'll be holding down the buttons to rotate the motor without any automatic stop detection. Once the valve is closed, I fully open the existing ball valve. My first observation is that it's leaking at the pipe connection, but otherwise the valve seems to be holding back the water just fine. Though soon enough some water does make its way out at the end of the pipe. This is about as much leakage as I anticipated, and I'd say it's within the requirement of being at most a trickle. I then open the valve a bit. The valve seems to be doing extremely average at its job, which is exciting because it means I may indeed be able to have shorter cycle times for my hydroponics. And that's what all of this is for, just so my plants spend a little less time with their roots underwater. Let's take a look at the leakage. The pipe connections are easy to fix with some sealant, and there's no surprise there. There's some water flowing through the pipe, which I'm guessing is from the valve not sealing perfectly. I declare that leakage acceptable. The most interesting leak is straight through the body of the 3D print. Almost all FDM 3D prints like this have some amount of porosity, and this leakage is to be expected. I may coat the valve in epoxy or something to keep the water from leaving the system. One place I don't see a leak is through the rod. That's surprising because the hole in the valve cover that it passes through is a direct path to water, but it's possible the Vaseline I put on the threads is doing a fine job of filling the gap. And that's the conclusion of the test. I'm out of time to work on this for now, and the algorithm I demonstrated to automatically close the valve is not robust enough to be deployed. I left the electronics in the cabinet, but removed the new valve, and will need to develop the algorithm further before it can run unattended. So how do I make the algorithm robust enough to run unattended? What could possibly go wrong with turn on motor and wait until threshold current? The first problem is ADC drift. I don't know if it was the Arduino's ADC drifting, the current sensor output drifting, or if the actual current consumption of the motor driver was drifting, but over the course of a day the idle value of the ADC rose above the hard-coded current threshold I had written. This resulted in the valve immediately thinking it was already closed when I asked it to close, and if the value had drifted in the opposite direction, then it's possible the controller wouldn't have stopped running the motor when it closed, and could have torn itself apart. I never expected the hard-coded threshold to be robust, but I'm still surprised it failed just sitting on my desk. One method I'll try to fix this is calculating the threshold relative to the ADC value prior to starting the actuation. Another foreseeable scenario is one of the little clay pebbles getting stuck in the valve. They could get under the gate and stop it from closing, above the gate and stop it from opening, or wedge somewhere in between and get it stuck partway. Roots could also gum it up, but wouldn't be as sharply detectable. For a current sensing based controller, this would likely result in degraded performance. The valve wouldn't open or close all the way, but would otherwise run just fine. If it were wedged part way, then it's possible the algorithm would immediately turn off the motor, meaning it just doesn't operate at all and stays jammed. There isn't really a solution to this, but you could at least detect it and notify the user. To detect it, you could time how long the valve takes to open or close. If it takes less time than usual, then it's probably because something's blocking the gate. To notify the user, you could at least have an LED to indicate that a fault occurred. That could signal the user to connect a serial terminal so the fault info could be printed out. If you get a Wi-Fi enabled microcontroller involved, then you could send the user notifications that they need to take a look at the valve. Mechanical failure is also something for the controller to consider. Mainly I'm thinking about the threads totally wearing out. In that case, the valve would fail to operate as the motor just spins around and the gate stays put. Additionally, I'm curious how the plastic gears will behave on a hot day. I don't know what to expect from PETG gears in the direct sun, and again, there's not a solution for this, but it's something you could detect and notify the user about based on how long the valve is taking to open or close. Another problem I anticipate is a long-term change in the nominal current draw of the motor due to friction in the system changing as a result of corrosion or debris accumulation. If the future motor nominally draws more current than the present motor, then the valve may not fully seat in position, and we may see greater leakage as the valve ages. I haven't given any thought to solving this because I don't know what it would even look like yet, but this is a great opportunity for data logging. Perhaps by recording the motor current each cycle, we'll be able to discover new trends. Looking beyond the valve, the Arduino is also monitoring the float switches. We detect several types of failures in the system just by timing how long it takes to cycle the water. In regards to the valve, you could detect that there's a jam if the tubs fill slower than they should, though a more likely cause for this would be running out of water. Either way, it's a condition that requires user attention and is something that is detectable. Finally, I just want to acknowledge that my current design is not weather resistant. Rain would be bad. At the very least, I'll print a simple cover to keep the rain off. Also, I didn't end up mentioning it on a slide, but one solution to many of these problems is to redesign the whole assembly to use a motor with less torque and have a less aggressive gearing ratio. Many of these problems would go away or at least not result in damage if the motor could be safely driven into a stall. My goal is to make this valve robust enough that I can just forget about it and let it run uninterrupted for years. If you have any input, please leave a comment. Thanks for watching.